Good, all right. Yep, cool. Oh, wait. I don't need to hear anything. Cool. All right. Sure. Yeah. Do that. Do that. That's okay. That's there. I'll grab a paper towel. But yeah, it's not going to still chapter 10.
Yeah, the code being, and then again, we're looking to double, what is it, something, format. Like.
So McCormick, Kendrick, whatever. Kendrick Lamar, yeah.
Just the double,
Okay.
the double like Cynthia, double like stable.
Okay, we can talk about that. Linearization is super straightforward. We can talk about it for sure.
He just, before it used to be like this part of the chapter, now it's like it's 10.4, and we're like, okay, that's
Interesting.
what we're getting quiz on is 10.4.
Okay, which is definitely the non-linear stuff, right? That's what 10.4 is. Okay. We can talk about non-linear things. Did they bring paper? I hope so. That's it.
That's 10.4.
The chapter, so section 10.4 is non-linear differential equations or system of non-linear differential
So
equations.
is that just not, is that not non-homogeneous?
Well, it could include non-homogeneous, but it's not typically. We'll do some examples. I would say I wouldn't expect it to be any non-homogeneous stuff there.
So there would.
I would say that they're homogeneous non-linear because meaning you don't have a constant somewhere out of that would be my expectation. Let's do that. In fact, yeah, let's I want to revisit the example we were doing at the end of class last time on Monday. Paper. I need paper. Actually need something to write. Bless you. Goodness gracious. Tomorrow has a leap day. February 29th. Fun fact. There won't be a leap year in the year 2100. Because it's all about making sure the seasons come out right. Like we don't want to get too far off because there's really like it takes like 365.2 something days to circle the sun, to orbit the sun. So every 4 years we have a leap year, except every 100 years we don't. except every 400 years we do. So that's why we had one in 2000. But there won't be one in 2100 or 2200 or 2300, but there will be one in 2400. Interesting. Interesting, useless information. Because calendars, I'm intrigued about calendars. I don't know why. It's just because I don't know. I was reading about it somewhere and I was like, oh, that's neat. Because calendars interest me. Also, I've talked about anchor days, right? Right? I haven't talked about anchor days. Oh. Am I recording? Good. Yeah, I'm recording. You can't. So I've slightly changed up how I'm doing this. It shouldn't really affect any recording. But now on my screen, I actually have different things on here. I'm not duplicating my screen. I am extending my screen to there, so you all aren't seeing. Like I can put this over here if you want me to, so you can see my face up there. But I don't think right. I mean, this little deal here. Yeah. Make sure I can be up there. I don't care. Cool. So Co-17C today is the 20th. Oh, anchor days though. I feel like I must have said this. So this year, the day of the week that's the anchor day week is Thursday. And all these days, 4/4, 6/6, 8/8, which is my birthday, 10/10, 12/12, are all on a Thursday this year. Next year, they'll all be on a Friday. Some other notable days, 9/5 and 5/9, 7/11 and 11/7, and the last day of February, which in a leap year is 2/29, and a non-leap year is 2/28. Also, Pi Day. So there's like a day in each month that you know is going to be on a Thursday this year. Kind of cool. Also Halloween, also Independence Day, also, and that's about it. That's my list. So when somebody asks me what day is Christmas on this year, I'm like, well, December 12th is a Thursday. 2 weeks after that is December 26th, which is also a Thursday. So Christmas must be on a Wednesday this year. That's how people do calendar tricks. Like they use this to be like, what day of the week is this particular date on? They're typically using this trickery. Okay, so back to what we were doing last time. We had these non-linear differential equations. dx1 dt equal to -5x1 plus x1 times x2, and dx2 dt was equal to x2 times, x2 minus 5x1 x2. Sorry, that's kind of gross. And we found the equilibria. We found that, so if you set them each equal to 0, well, this first one is going to factor out the x1. You've got -5 plus x2. This one down here, if you factor out the x2, you're going to get x2 times 1 minus 5x1. So from this first equation, equal to 0, sorry. In the first equation, you either get x1 equal to 0 or x2 equal to 5. I'm going to say every time, this doesn't mean that 0, 5 is necessarily an equilibrium. It probably isn't. It isn't. Because if you plug in x1 equal to 0 and x2 equal to 5 down here, you don't get that equal to 0. So we have to look at both equations being 0 at the same time. So if we take the second equation, if we plug in x1 equal to 0, I'm going to get x2 times 1 minus 0 equals 0. So x2 is also going to have to equal 0. So this gives me that 0, 0 is an equilibrium. And also, if I plug in x2 equal to 5, if I plug in 5 here, I'm going to get 5 times 1 minus 5x1 equal to 0. So the 1 minus 5x1 has to equal 0. So that 5 times 0 will give me 0. So I've got 1 minus 5x1 equal to 0. 1 equals 5x1. x1 equals 1/5. So the other equilibrium is going to be x1 is 1/5. x2 is 5. And those are the only two equilibria of this system. Okay. So now I'd also like to find the linearization of this system. Well, then we'll talk about classifying the equilibrium. We'll talk about the linearization, but I feel like we should do the linearization first. So the linearization, I'm going to kind of do this the long way the first time, just so you can kind of see where it's coming from. So we're gonna linearize each of these differential equations. So first we're gonna linearize dx1 dt equal to negative 5x1 plus x1 x2. And so the thing here is, where are we linearizing? Well, you can linearize at any equilibrium. You can actually linearize anywhere, but we only linearize at equilibrium. So here's what we're going to do. We're going to find that our linearization here, which we'll call L1, yeah, sorry, I'm trying to think about what notation I want, yeah. So sorry, I'm trying to think about what I want. Yeah, sure. So the linearization L of x1 comma x2 is going to equal my function at x1 comma x2. Hold on, I know we haven't said what that is yet. Plus the partial derivative of my function with respect to x1 times x1 minus x1 hat plus the partial derivative of my function with respect to x2 times x2 minus x2 hat, where f is what I'm calling this first equation. It's very similar to the linearization formula we used before, where you're essentially evaluating your function of two variables at the point of linearization, and then you're doing the partial derivative with respect to x times x minus the x coordinate, plus the partial derivative with respect to y times y minus the y coordinate. I'm just using x1s and x2s instead of x's and y's.
Did you do the linearization twice to get to equilibrium?
Yes, and that, well, yes, we'll do all the things, but yes, we're gonna end up doing it twice, kind of. So, but I'm showing you kind of this longer way first, so then we can talk about the nicer way to write it. So let's do it at 0, 0 first. So at 0, 0, we're gonna say that the linearization of x1 comma x2. Yeah, I don't love my notation there, but fine. It's going to be f of 0, 0, which should always be 0. If I'm plugging in the equilibrium, then f of the equilibrium, I should get 0 every time, no matter if it's this equilibrium or that equilibrium. Now my partial derivative with respect to x1 is going to be negative 5 times negative 5 plus x2. So I'm going to do negative 5 plus x2. I'm plugging in 0, 0 times x1 minus 0 plus fx2. I'm taking the partial derivative with respect of f with respect to x2. I'm getting x1. I'm plugging in 0, 0 times x2 minus 0. So here's what this ends up looking like. My linearization here, which I guess I should be calling L1 because I'm going to do another one which is called L2. So let's call this L1. Sorry about that. It's going to be 0 plus negative 5 plus 0 times x1 minus 0 plus 0 times x2 minus 0. So really my first linearization here is just kind of boring. It's negative 5x1. Let's do the linearization at 0, 0 of the second differential equation. Bless you. So now we're going to linearize g of x1 comma x2. That's what we're going to call the second differential equation, which was x2 minus 5x1 x2. And if I was being a little bit smarter about the order I was doing the work in, I'd probably find the partial derivatives first. So I'm going to find real quickly here gx1 equal to 0 minus 5x2. And the derivative of g with respect to x2 is 1 minus 5x1. And so then if I do gx1 evaluated at 0, 0, I know I'm going to get 0. Gx2 evaluated at 0, 0, I know I'm going to get 1 minus 0. So my second linearization, or the linearization of the second equation at the same point 0, 0 is going to be g of 0, 0 plus my gx1 at 0, 0 times x1 minus 0 plus gx2 at 0, 0 times x2 minus 0. Which ends up being g of 0, 0 also 0. Gx1 of 0, 0 is going to be 0. And gx2 of 0, 0 is 1. So also unexcitingly, we get x2. Okay. We don't usually do it this way because it's a kind of tedious and cumbersome. What we're really going to do, instead of doing what we just did, is we're going to find the Jacobian. So here's what here's what both linearizations are going to look like at the same time. So the linearization L1, L2 as a vector is going to be f of x1 hat, x2 hat. Oh, I should have been using hats. I'm sorry. Right, because we're playing in equilibrium and the equilibrium are hats. Pretend there's hats on all of those. Okay, fine. There should be a little hat here. And there's actually not that many hats to put back in. No, that's kind of it. I think I only missed one hat. I'm okay with that. Okay. So the linearization as a vector is f of x1 hat, x2 hat, g of x1 hat, x2 hat, which again is always going to be 0, 0. Because if you're plugging in the equilibrium, f is going to be 0, g is going to be 0. Cool with that? Okay, I can say more about it if I need to. Plus, then we're just going to have the Jacobian. fx1, fx2, g with respect to x1, g with respect to x2, times the matrix x1 minus x1 hat, x2 minus x2 hat. And then this here, right, this is the Jacobian, and this is the Jacobian evaluated at whatever equilibrium we happen to be using at x1 hat, x2 hat. So check it out, right? If you think about how this multiplies out, I'm literally getting the same thing I had up here for L of x1, x2, right? I'm getting f of x1 hat, x2 hat. I'm getting fx1 times x1 minus x1 hat plus fx2 times x2 minus x2 hat. And in the second row, I'm getting the same thing for the g's. I'm getting g of x1 hat, x2 hat, right? So right up here, so they plugged in my numbers, plus gx1 times x1 minus x1 hat plus gx2 times x2 minus x2 hat. So this is the condensed matrix way of writing the linearization of your system of differential equations. I should really say the condensed way of writing the linearization of your system of non-linear differential equations, because you wouldn't linearize something that was already linear. It's already linearized. So this process is only necessary for when you have non-linear differential equations. So just to kind of come full circle here, our Jacobian, we should already be able to write out because we already have all our partial derivatives, but let's write it out anyway. Our Jacobian would have been the partial of the first thing with respect to f with respect to x1, which is -5 plus x2. And then the second coordinate would be x1. And then the second row first entry would have been -5 x2. And then the other one would be 1 minus 5x1. Which are all the partial derivatives we saw when we did this. Yeah, I'm looking to clarify here. Yep, that's exactly what I'm seeing. -5x2. Yep, cool. Good. All right. So we could have instead set our linearization at 0, 0. L1, L2 was equal to 0, 0. Not because it's 0, 0 there, but because when we plug in 0, 0, we get 0, 0. And then plus this Jacobian matrix evaluated at 0, 0. Times x1 minus 0, x2 minus 0. And those are exactly the same linearizations we got before, right? L1 ends up equaling 0 plus -5x1 plus 0x2. L2 ends up equaling 0 plus 0x1 plus 1x2. And even though they're kind of boring linearizations, they are the same linearizations we just wrote down doing them separately. I'm just looking back and checking. Yep, our linearization for L1 was negative 5x1. Our linearization for L2 was x2. Exactly what we're getting there and there. Cool. The nice thing about doing it this way is then it's easier to do all the other ones as well. So for example, if instead I want to do the linearization at my other equilibrium, which I forgot what it was 1/5 comma 5. Well, I'm just going to say, great, my linearization there is going to be, I'm still going to get 0, 0. Right, because when I plug in that point to my f and my g, right, this is really f of 1/5 comma 5. That's really g of 1/5 comma 5, and it better be 0. Otherwise, it's not an equilibrium. Plus my Jacobian, but now I'm taking my Jacobian evaluated at this point. So it's going to be negative 5 plus 5, 1/5, and then negative 5 times 5, and then 1 minus 5 times 1/5. Times x1 minus 1/5, x2 minus 5. It's a little more interesting when you have a non-zero zero equilibrium. So we end up getting 0 times x1 minus 1/5, 1/5 times x2 minus 5, and then negative 25 times x1 minus 1/5. So there's the linearization for the first differential equation at the point 1/5 comma 5. There's the linearization for the second differential equation at the point 1/5 comma 5. But it really just boils down to saying it's the Jacobian evaluated at your point times the vector x1 minus your point, x2 minus your point. Not too terrible when it all comes down to it. I think I remember last time I said I was going to do something like graphs. I think I remember saying something about how I was going to graph the thing. Does that sound right? I seem to recall that. We'll do that in a second here. Oh, no, that's the problem. What did I do? Oh my gosh, I've ruined it. I've ruined everything. What is going on? Where did that come from? I have no, I pressed Control T and that's what popped up. Also, I should fix this here. It's really hard to see. I can see that. I can look at the controls right there. I'm so dumb sometimes. The problem is in the other classroom that this thing is broken, so I can't look there to see it. So I'm like, oh, okay. And then we also talk about classifying the equilibria. So I'll point out that for both of these, well, actually for this one, it's really easy to classify the equilibria. We know that for 0, 0, we definitely have instability, because if we look at the eigenvalues of our Jacobian, the eigenvalues would be equal to negative 5 and positive 1, meaning we would have something saddle-ish at that point there. And then for the other one, I think we talked about how it was kind of like a center, but we couldn't really be sure. If you find the eigenvalues here for 1/5 comma 5, you get the determinant of, well, you get negative lambda times negative lambda. Sorry, determinant of negative lambda 1/5, negative 25, negative lambda. You get lambda squared minus 1/5 times negative 25. That's gonna be plus 5. So you're gonna get purely imaginary eigenvalues. You're gonna get lambda squared equal to negative 25, sorry, negative 5, and then lambda is gonna be plus or minus the square root of negative 5. So we can't really determine the stability there because, again, of the localness issue. But if we look at it, I think it's kind of cool. Let me see if I can pull up. Oh my gosh, maybe that's the problem. This is my cursor always ends up over there. I'm like, where's my cursor? If we pull up my favorite graphing thing. So we have our differential equation is negative 5 times x. Sorry, I should have had this ready to go ahead of time. Plus x times y. And then our second one is y minus 5 times x times y. Let's see what happens when we graph this sucker. Ooh, that looks wild. No, you just, I'm just, yeah, once, oh my God, wow, this looks bonkers. One second. Look at that. Crazy looking, right? So again, right, over here near the origin, we have kind of saddle-ish behavior. That looks really, did I type it? Let's make sure I typed it in right. Well, so looking at back at our differential equations, right? I should have -5 times x plus x times y, and I should have y minus 5 times x times y. No, that seems like it looks right. But again, right, that's why nonlinear stuff is so weird, because like near the origin, you've got saddle-ish behavior, but if you move too far away from it, then things start looking not saddle-y. And then my other equilibrium point, which was, I forgot what it was. What was it? 1/5, comma 5. So over here at 1/5, comma 5, somewhere like up there, that's where you should have like center or neutral spiral behavior. We might need to zoom, we might need to change our y minimum max. Let's change the maximum to like 10. Sorry, it's hard to see. I should look there. I could look there. Sorry, it's hard to get used to looking there. So then if we look here at like 1/5, 5, right here, yeah, you can kind of see your neutral spiral behavior there, which is not really stable or unstable. It's kind of okay. So before we do another one, questions about this. Yeah, let's do another one. I've got another one all ready to go here. I can remember where I put it. I know where I put it. Right. Cool. This is a good one. I like this one. So let's say we have the following system of non-linear differential equations. And I guess we should use x. I really would love to use x's and y's because that just feels more normal. But he really is using x1 and x2 like all the time, right? Yeah. Then we should stick with x1 and x2, despite me not loving it. So here's our next situation. We've got dx1 dt equal to 10x1 minus x1 squared minus 2x1 x2. And we've got dx2, excuse me, dx2 dt equal to 10x2 minus 2x1 x2 minus x2 squared. And usually get in the habit when you're dealing with these nonlinear differential equations, your habit should be to call the first one f and the second one g. Always what we're going to do. I would also make an observation here, which is sometimes true. These equations happen to be symmetrical, meaning that if you interchange the x1 and x2, the equations would still be the same. If I replaced x1 with x2, I'd have dx2 dt equal to 10x2 minus x2 squared minus 2 times x2 times x1. It's this, they would switch. So if you interchange x1 and x2 and you still get the same set of equations, here's what that means. It means all of your equilibria have to be paired with the interchange. So for example, if 2, 7 was an equilibrium, so is 7, 2. That's guaranteed if you see that you have symmetry like this. It's kind of nice. But again, not something you have to be aware of, just it's cool to know. So let's go ahead and find the equilibria. Now, normally I would say we should look at the one that's easier, but since they're essentially the same equation, they're both as easy as the other one. So let's just pick the first one. And looking at the first one, if I set that equal to 0, I am observing that I can factor out an x1 from each of those terms. So I'm going to have x1 times 10 minus x1 minus 2x2 equal to 0. So I'm either going to get x1 equal to 0, yay, or 10 minus x1 minus 2x2 equal to 0, which is a little bit less easy to deal with. If I was graphing some null clines, because might as well graph the null clines as well. X1 equal to 0 is my y-axis. And then 10 minus x1 minus 2x2 equal to 0. When I graph this, I'm thinking of x2 as being my y. So I'm really thinking of 10 minus x minus 2y equal to 0. So that I have 10 minus x divided by 2 equal to y. So I'm graphing like y equal to negative 1/2 x plus 5. So maybe it looks something like this. My intercept here would be 0, 5. My intercept here would be, what would it be? 10, 0. Okay, let's look at the other equation. So my other equation is, I can factor out an x2. You get x2 times 10 minus 2x1 minus x2 equal to 0. And I get very similar null lines here. Here I'm going to get x2 equal to 0, which is this line here. And I'm going to get this other thing here, 10 minus 2x1 minus x2 equal to 0. And again, I'm thinking of this as 10 minus 2x minus y equal to 0, or 10 minus 2x equal to y. So this graph would have a y-intercept of 10 and an x-intercept of 5. Of course, I've drawn this a little bit off the chart here. So it looks something like this. And I should have used different colors. So let me do a little bit more labeling here. So I just want to point out that this line here, this is an x2 null line. And so is this line here. Whereas this line here is an x1 null line. And so is this vertical line here. And the thing that's neat about equilibrium is you get equilibria exactly where an x1 null line intersects an x2 null line. So we're going to get an equilibrium here, here, be careful, x1 and x2 here, and x1 and x2 here. So these 4 points are all equilibria. And 3 of them are easy to see what they are. 0, 0, I think is pretty obvious. 0, 10 is not too terrible, and 10, 0 is not too terrible. You can also get them by doing the usual thing, where I could take this x1 equal to 0 and plug it. Well, in fact, let me say a little bit more here. Dealing with this situation, we need one of these two things to be equal to 0, and we need one of these two things to be equal to 0. So there's 4 different ways we compare these things. That one and that one, where both x1 and x2 are 0. That one and that one, where x1 is 0 and 10 minus 0 minus x2 equals 0, which would give you x2 equal to 10. Or that one and that one, which is going to give you x1 equal to 10. Or this one and this one, which is the one that's a little bit challenging to figure out. So basically our equilibria are going to be x1 equal to 0 and x2 equal to 0, or x1 equal to 0 and 10 minus 2x1 minus x2 equal to 0, which gives you x2 equal to 10 because we plugged in 0 for x1, and then x2 equal to 0 and 10 minus x1 minus 2x2 equal to 0, which gives you x1 equal to 10. And then finally, the hard one, where you pair the equations with each other. So the last one is going to be 10 minus 2x1 minus x2 equal to 0, and 10 minus 2x1 minus x2 equal to 0. Essentially, trying to find this point where those two lines intersect. So do this however you like. I would probably solve this for x2 and say 10 minus 2x1 equals x2, and then plug that in for x2 over here. I feel like I wrote the same equation twice. I did. I should have said 10 minus 10 minus x1 minus 2x2 equals 0. So plug that in here and get 10 minus x1 minus 2 times 10 minus 2x1 equals 0. With a little bit of algebra, we have 10 minus x1
minus 20 plus 4x1 equal to 0. Negative x1 plus 4x1 is 3x1. 10 minus 20 is negative 10. So then 3x1 equals 10, or x1 equals 10/3. If you plug that back in over here, 10 minus 2 times 10/3 is going to be 30/3 minus 20/3, which is 10/3. So my last equilibrium is 10/3, comma 10/3. It's a lot of equilibria. Okay. Let's talk about classifying. So our equilibria are 0, 0, 10, 0, 0, 10, and 10/3, 10/3. To classify them, we need to find the Jacobian. So we're going to classify. Before we can start classifying, we need the good old Jacobian, which is our fx1, fx2, gx1, gx2. So looking back at our original system of differential equations, going to help us out here. Sorry, I'm all over the place. I don't think we need to write them down again. We just need to be like, okay, fx1. Like, why don't you guys find the Jacobian? Yeah, you all should find the Jacobian right now. So the first, I'll give you the first term. fx1 is going to be 10 minus 2x1 minus 2x2. You have 3 more things to fill in. So I just took the partial derivative of f with respect to x1, and that's what I got. So now do fx2, gx1, gx2. Shouldn't be too terrible. In fact, fx2 is a lot nicer than fx1. All right, let's follow the rest of it. So fx2 is super nice. Partial derivative of f with respect to x2 is 0 minus 2 times x1 times 1. Gx1 is similarly nice. The partial derivative of g with respect to x1 is 0 minus 2 times 1 times x2. And then minus 0. And finally, gx2 is similarly less nice. It's going to be 10 minus 2 times x1 times 1 minus 2 times x2. So there's our Jacobian. And now we're going to evaluate the Jacobian to each of the four equilibrium. They feel very much like critical points with their equilibria, but it's kind of the same idea. We're going to evaluate this at each of our 4 equilibria to try and determine the stability or instability. And again, I would really encourage you to use the words stability or instability, not it's a saddle, it's a node, it's a spiral, because it's kind of not really what's true. It's locally that, but really we're just trying to determine stability. So let's look at 0, 0. J of 0, 0 is 10, 0, 0, 10. So if you were going to talk about what kind of thing you had, you would say that you had what? A node, a spiral, or a saddle? We have a node because our eigenvalues would be both positive 10. So you should say then that we know that this is going to be, so 0, 0 is unstable. Sorry, I didn't talk about the stability. Both eigenvalues are positive, so it's unstable. But really, I would say this is because the trace is positive, and the determinant is also positive. You only get stability if the trace is negative and the determinant's positive. Okay, so let's look at J of 10, 0. So J of 10, 0 is going to be, let's see here. 10, so I'm plugging in 10 for x1. So 10 minus 20 minus 0 is going to be negative 10. And then a 0, no, sorry, 10. I'm plugging in 10. So I'm going to get a negative 20 there. But I'm going to get a 0 here, which is good for me. And then I'm going to get a 10 minus 20 minus 0. So a negative 10 again. And here we can say that our point 10, 0 is, well, our trace is negative. Our determinant is still positive because the determinant's 100 minus 0. I should probably calculate them instead of just saying what they are. So this is going to be stable. But you could have thought of it as having two negative eigenvalues. So we would have had something that looked like a stable node. Okay. We'll probably get the same thing being true for 0, 10. Let's find out. So if I plug in 0, 10, I'm going to get 10 minus 0 minus 20. I'm going to get 0 here. I'm going to get negative 20 down here. And over here, I'm going to get 10 minus 0 minus 20. So I would say that my trace is negative 10 plus negative 10, which is negative 20, which is negative. And our determinant is negative 10 times negative 10 minus 0 times negative 20, which is 100, which is positive. And so we again meet the condition for stability here. We are stable. If you wanted to, you could totally think about this as having two negative eigenvalues, so it feels like it's a stable node locally. Okay, finally, the last one. 10 thirds comma 10 thirds, which is probably going to be the hardest one to evaluate. So we plug in 10 thirds, I mean 10 minus 20 thirds minus 20 thirds. So 10 minus 40 thirds, 30 thirds minus 40 thirds is negative 10 thirds. And then over here, I'm going to plug in 10 thirds and get negative 20 thirds. Same deal down here. And if I didn't get negative 10 thirds here, I'd be very surprised. We'll check 10 minus 20 thirds minus 20 thirds is again negative 10 thirds. For this one, we can't just see the eigenvalues from the get-go. Not that we've actually been doing that, but we've kind of been doing that. So here, if you wanted to do it this theorem 16 sort of way, let's do it that way. So our trace is going to be negative 10 thirds plus negative 10 thirds, which is negative 20 thirds. Good. So far, we're on the track for stability. Let's talk about our determinant. Our determinant is going to be negative 10 thirds times negative 10 thirds, which is 100 over 9, minus negative 20 thirds over times negative 20 thirds, which is 400 over 9, which I don't really care that it's negative 300 over 9 or negative 100 over 3. I care that it's negative. And if your determinant's negative, what do we say? Unstable. And yes, you could say if it was actually linear, you could say we have a saddle, but we have something saddle-esque at that equilibrium. But yeah, we're going to say we have an unstable, or I should say that, I should have said here, right? 0, 10 is stable. Here I should say 10 thirds comma 10 thirds is unstable. Because we have a saddle-like thing. Not satellite, saddle-like. Yeah, I know. Okay. Before we talk about the linearization of this stuff, any questions about what we've done here? The 10 thirds, 10 thirds? Sure. So what I did was I took, so basically I'm trying to find, so I took my, yeah. So for each of these equations, I'm setting one of the factors equal to 0. So the first 3 points are easy to get. I set this factor to 0 and this factor to 0, and I get 0, 0. I set this factor to 0 and this factor to 0, and I get 0, comma 10. Because if x1 is 0, and I plug that in here, then x2 has to be 10. Similarly, to get this point over here, I set x2 equal to 0, and this factor equal to 0, and I get 10 minus x1 minus 0 equal to 0. So I get x1 equal to 10. And then for the last point, which is setting this factor equal to 0 and this factor equal to 0, we have to do some solving systems here. So what we did was and I messed up here, I wrote the same equation twice accidentally. So when I set each equation equal to 0, the 10 minus 2x1 minus x2, and the 10 minus x1 minus 2x2. And then I solved this equation for x2, plugged that into the x2 in the other equation. So then I had 10 minus x1 minus 2 times 10 minus 2x1. Multiplied it out, collected terms, ended up having 4x1 minus x1, so 3x1, and 10 minus 20 is negative 10. So then I added 10 divided by 3, and you got x1 equal to 10/3.
So you just pick and choose like what x1 is this, what's the other.
Right, yeah, and then I plugged that back into the other equation here and got x2 equal to 10 minus 2 times 10/3, which also ended up being 10/3. Which wasn't surprising because we knew from the symmetry, right? So I'll say the thing I said before, which is that all of my points either have the same x and y value, or you have another point that has the interchange, right? I have 0, 0, I have 10/3, 10/3, and I have both 10, 0 and 0, 10. Not unexpected at all. Kind of neat. All right, what if I wanted to do the linearization of one of these things? What if I wanted to find the linearization of this system? So I want to find the linearization of the dx1 dt equal to, I'm going to write this down all again, it's terrible, equal to 10x1 minus x1 squared minus 2x1 and dx2 dt equal to 10x2 minus 2x1 x2 minus x2 squared at 0, 0. Well, the nice part is we've already done almost all the work, right? The linearization here, my L of x1 comma x2, which is just L1, L2, is going to be my Jacobian evaluated at my equilibrium times x1 minus the x1 coordinate, x2 minus the x2 coordinate. And I already found the Jacobian, right? We did that work already. So looking back at my Jacobian for 0, 0, I can see that, great. The linearization here is going to be 10, 0, 0, 10 times x1 minus 0, x2 minus 0. Or kind of unexcitingly, 10x1 and 10x2. Kind of boring. But again, we don't really care if it's boring or not. Let's look at a couple more just because we might as well at this point. Again, if you've already classified all the equilibria, the linearization aspect of this is not hard to do. Or you've done all the work you already needed to do. So then if we want to do the linearization at, say, 10, 0, same formula, except now it's going to be my linearization is going to be my Jacobian at 10, 0 times x1 minus 10, x2 minus 0. So then it's going to be my Jacobian there, which was -10, -20, 0, -10 times x1 minus 10, x2 minus 0. And then you could write it out. I mean, I think I would leave it like this, but you could totally do the multiplication a little bit and say you've got -10 times x1 minus 10 minus 20 times x2 minus 0. And then in the second row, you have 0 times x1 minus 10 minus 10 times x2 minus 0. So what we're kind of thinking of here is that, no, I don't want to say that. Never mind. That's that. I don't want to make it more complicated. We might as well. So I'll say that the third one should be pretty similar to the second one here. The linearization at 0, 10, I wouldn't be surprised if it was almost exactly the same or kind of flipped. Let's do it anyway. So the linearization at 0, 10, sorry, that's bad notation, James. The problem is when you're writing the linearization, the linearization is still a function of your variables. You don't write the linearization at 0, 10, right? 0, 10, and then the linearization of x1 comma x2. It's going to be your Jacobian at 0, 10 times x1 minus 0, x2 minus 10. And then that's just going to be negative 10, 0, negative 20, negative 10. I know it's kind of boring. And let's just leave it like that. I don't think we need to multiply it out. And finally, the third one, which might be the most interesting, the linearization at 10 thirds comma 10 thirds is going to be, I really think if you get asked this, it's worth writing out this first part here. The Jacobian at the point times x1 minus the x1 point, x2 minus the x2 point. And then that's going to be the actual Jacobian, which is negative 10 thirds, negative 20 thirds, negative 20 thirds, negative 10 thirds, times x1 minus 10 thirds, x2 minus 10 thirds. Cool. The linearizations are not that bad. They're really just take the Jacobian at the point you're linearizing at, and then multiply that Jacobian by the vector x1 minus the x point, x2 minus the x2 point. And I'll point out that technically there is the f of 10 thirds comma 10 thirds and the g of 10 thirds comma 10 thirds out here. But we know that every time that's just going to be 0, 0. Because you're literally plugging in the equilibrium, and the equilibrium points are found by setting each of those equations equal to 0 in the first place. So if they're correct, plugging them back in should yield 0. Cool. How much time? I don't have a lot of time. Okay. Let's let me just, I'll give you 3 minutes. And stop there, I guess. Unless you have, so let me ask, do you have any questions, clarifications, things you would like me to say more about that I might have forgotten about? It's okay if you don't, but like but you've got 3 minutes to kill. What do you want me, what do you think? What are your concerns? Observations? Thoughts? I'll shut up. So that matrix is coming from that. So that's just the Jacobian, which we already did before. So normally you would have to do that work. I was just saying we've already done the Jacobian before when we were trying to determine the equilibrium, classify the stability or instability of each equilibria. So I wasn't going to do that work again. I was saying, oh, here, and again, we found, right, find the Jacobian. It's just the, yes, let's go back here. Sorry, I'm thinking a little bit out of order here. Apologies. To find the Jacobian, we're just finding the 2x2 matrix of partial derivatives. So your first equation is f, your dx1 dt equation is f, your dx2 dt equation is g, and then we're taking the partial derivatives of f with respect to x1 and x2. The partial derivatives of g with respect to x1 and x2. And then after we find the general Jacobian for any x1, x2, then we're just taking each equilibria and plugging that into the Jacobian. So to find this matrix here, I took that point, plugged it into this matrix, and got 10 minus 0 minus 0, 0, 0, 10 minus 0 minus 0. That's what I got. Or I plugged in this point, 10 comma 0, and got 10 minus 20 minus 0, negative 2 times 10, 0, and 10 minus 20 minus 0, which is negative 10. So I'm just plugging in the equilibria to the Jacobian. And then after I have that, I'm using that matrix then to do my linearization. So, but by the vector, you mean like this vector here? Yeah, it's always x1 minus, that's good point. Always that. So when it's 10, 0 here, that's why it's x1 minus 10, x2 minus 0. Always. Kind of like how before when we did the linearization at a point, you always did taking the derivative and multiplying it by x minus that point. Because essentially you're finding, it's really just like the equation of a line. It's y minus y1 equal to the slope times x minus x1. This is like your x minus x1 and your x minus and your y minus y1. Yeah, good question. All right, I killed 3 minutes. Great. It's 2 o'clock. Have a lovely rest of your day. Good luck on your quiz tomorrow. I have office hours over in C class right now, and tomorrow in C class in the morning and CADs in the afternoon. So if you want to come find me, come find me.
Class,
Yeah, on Tuesdays and Thursdays, I'm in C class from 9 to 10:15-ish.
God dang it.
Yeah. It is important to go to class. Bye. You're very welcome. Later, Maggie. And stop.